solubility of a solute is the maximum amount that can be dissolved in a specified amount of solvent, which depends on the nature of solute and solvent, condition, temperatures and pressure, presence of any solubilizing agent, any agent that helps to improve the solubility of one particular component, or stabilizers we are just talking about. On addition of a solid to solvent, solute, what happens? Molecules separated, they moves to a bulk of solvent, and its concentration increases in solution. This process is known as dissolution. So basically, dissolution is first when we put a solute into it. I'm talking particularly here ionic solute. When it goes into our solution, it got separated into its ions, and ions moves into a bulk solution, and homogenized. The process of separation and homogenization of these ions into a bulk of solvent is known as dissolution. Before we'll go ahead into a dissolution, we should understand there is an important concept in solutions: like dissolves like. Polar solutes dissolves in polar solvents, and non-polar solutes better dissolves in non-polar solvent. This is known as concept of like, dissolve like. Dissolution and crystallization. We know when we initially start putting solute in solvent, it dissolves in it. But after some time, some solute particles in solution collide with each other and start adhering and get separated out of solution. This process is known as crystallization. So after dissolution, certain solubilized particles will collide, adhere, and come out of solution, known as crystallization. Crystallization is basically precipitation. Phenomena of dissolution and crystallization are dynamic in nature. On addition into a solvent, dissolution of solute will be faster in the beginning. As more and more solute solubilized, dissolution starts to approach crystallization. So what we see, solubility will reduce with time, crystallization will increase with time, and at one particular stage, both rate of crystallization and dissolution will be equal. That point is called equilibrium point at a particular temperature. Concentration of a solution at equilibrium is called saturated concentration. Means when we say, when we start pouring, let's say we take a cold water, we start putting a sugar into it. We keep on pouring our sugar into it and it dissolves maximum quantity. But after a certain time, we will see sugar is not dissolving. Whatever sugar we add, it will stay there on top. That's what happens is saturated concentration. Means water cannot take any more sugar in it. But what actually happening at molecular level? At molecular level, both dissolution, means the sugar going into water, and crystallization, sugar coming out of water as a solid, they become equal. And that's what we're calling a dynamic phenomena. And the concentration at that point is called saturated concentration. An unsaturated solution is one in which more solute can be dissolved at the same temperature. Effect of temperature on dissolution. Dissolution is a dynamic equilibrium and follow Lee-Chatelier principle. So what is the effect of it on temperature? For nearly saturated solution, dissolution process is endothermic. Energy supplied in raising the temperature will be used in solubilizing more solute, which means for saturated solution, it's an endothermic reaction. If we supply more heat to a solution, mean we raise the temperature of a solution, then more and more of solute will go into a solution because that's follow the endothermic principle. Lee-Chatelier principle says for endothermic reaction, if we supply it heat, then reaction will go in forward direction. Dissolution. For exothermic reactions, rise in temperature will reduce the solubility of solute. Now, if the reaction is exothermic, in such a case, the rise in temperature will create more and more precipitation or crystallization. Effect of pressure in solubility of solids. Now, as we know, solid and liquids are highly incompressible. So, for all practical applications, we can consider solubility is not affected by the change in pressure for solids. Now, solubility of a gases and liquid. We know gases are compressible. So, solubility of a gas is increased with increase in pressure. Increased pressure, what happens? Increases the number of particles of gas present per unit volume over the solution. Here are the gases present. If we apply a pressure here, same gas is squeezed in a smaller volume, mean number of gas atoms or molecules per unit volume increases. So this increased number of gaseous atoms or molecules strike more number of times on the surface of liquid. The average striking frequency increases on the surface of liquid, which means the probability of going a particular atom into a gaseous liquid increases. Here is a systematic law to explain the solubility of gases in liquid. The partial pressure of a gas in vapor phase is proportional to the mole fraction of the gas in solution. So partial pressure of the gas in vapor phase is proportional to the mole fraction of the gas in solution. P is the partial pressure, KH is our Henry's law constant, X is mole fractions. Here we see these are different temperatures, gases. So partial pressure of a gas vapors is proportional to mole fraction of the gas in solution. Henry's constant. Here is the Henry's constant, we explain it. KH increase with rise in temperature. Solubility falls with rise in temperature for gases. So solubility, here is a solubility constant, Henry's constant. It increases with rise in temperature. Here we see for the same gas, oxygen, At higher temperatures, the Henry's constant value will be higher. Now in Henry's, when this is a constant value, for partial pressure is same. When temperatures goes up, KH will go up. It means X will have to come down to compensate the increase in KH. So mole fraction in solution will reduce with increase in temperature because of higher Henry's constant. Here we see nitrogen. Henry's constant will increase with temperature. For same thing with oxygen. So Henry constant is directly proportional to temperature. And partial pressure of a gas over the solution is inversely proportional to Henry's constant, which is directly proportional to temperature. So higher the temperature, lower will be the partial pressure of gas above the liquid surface. Smaller will be the mole fractions in solution. Let's take an example. We know H2S gas, which is a rotten gas, like rotten egg smell, is used for qualitative analysis of lead. If solubility of hydrogen sulfide in water at STP conditions is 0.195 molar, we have to calculate the Henry's law constant. Let's explore it. We know it's a molality, which means 0.195 moles of H2S present in 1 kg of water. Molarity of number of moles of water is 55.55 in 1 kg. Number of moles of H2S we know. So its mole fraction will be mole fraction of this will be H2S will be 0.195 divided by 0.195, 55.55, which means 0.0035. That's a mole fraction of H2S. Under STP conditions, which is at 1 atmospheric pressure, 0.987 bar. We convert atmosphere into bar. Now, this is a partial pressure of H2S above that solution surface. We apply Henry's law. H2S pressure is 0.987. KH we want to find out, mole fraction we have it. So we get the value of KH as 282 bar. That's Henry's constant. And unit of KH is Henry's constant is pressure. Here we want to make an important declaration. We have used under our calculation STP as 1 atmosphere, but IUPAC has made certain changes in that STP definition in 1982 or 1988, which defines as STP a temperature of 273.15 Kelvin or 0 degrees Celsius, and pressure will be 1 bar, which is nothing but 1 lakh Pascal. Now, applications of Henry's law. First, solubility of CO2 in soft drinks or soda water. We dissolve our carbon dioxide in water at high pressure, because we know higher the pressure over the surface, more amount of carbon dioxide will go into solution. That's Henry's law. Another example is scuba diving. We know scuba divers use air cylinders that is filled with diluted air and diluted with helium helium is 11.7%, 32% oxygen, 56% are almost nitrogen. Why it is done? The reason is fairly simple. We do it because we know under the water there is a high pressure on scuba divers, and under high pressure more and more gas will be dissolved in their blood. Now if scuba diver suddenly comes out, the gas will almost immediately try to come out of their blood and create cavitation. The cavitation can really make divers sick, or it can be even fatal for their health. But if we will dilute it with helium, which having a poor solubility in blood, even under the pressure that the divers face under the surface, that's why we dilute it with helium. Another application is, or we can say implication, high altitude sickness known as anoxia. What happens? We know that at high altitudes air is thin, so under the reduced pressure we are not getting the sufficient oxygen in our lungs, or the pressure of the oxygen is not sufficient for dissolution in our blood. Under such a condition, what happens? We are not getting sufficient oxygen supply to our cells, and that is the reason for dizziness or sleepiness. Our consciousness will reduce. All these symptoms of anoxia. This is the implication of, again, Henry's law.